Hi, I'm Amy and this is my final project for the UCL module, Artificial Intelligence for Earth Observation. This project compares two different machine learning approaches for classifying land cover in urban areas, using Sentinel-2 satellite imagery over Waltham Forest, London from 2020 to 2024. My aim was to explore how different algorithms interpret complex city environments and how this affects both performance and environmental cost. Machine learning can help us classify satellite images by learning patterns in spectral data, but how we guide that learning changes everything. Supervised learning uses labeled examples. We tell the algorithm, this pixel is urban, this is vegetation, and it learns from those labels to classify new data. The random forest algorithm is a classic example. It builds many decision trees and lets them vote. Unsupervised learning is different. It doesn't use labels at all. Instead, it finds structure in the data, clustering similar pixels together based on their spectral values. K-means is a common unsupervised method. It assigns pixels into K-groups, then iteratively adjusts the grouping to minimize variance within each cluster. Each method has its strengths. Supervised models provide clearer, semantically meaningful outputs, but require training data. Unsupervised models are faster and more flexible, but need interpretation. So now let's move on to the code itself. We use Google Colab as it offers free GPU resources and works on your web browser, so there's no installation required. So as usual, you want to make sure you don't skip running the setup code block, so this includes mounting to your Google Drive, importing required packages, and double checking paths. These steps are all provided at the top of each notebook. We use Sentinel-2 Level 2A surface reflectance data for the years 2020 to 2024, focusing on 6 key bands, blue, green, red, NIR and 2 SWIR bands. We also calculate the NDVI and NDVI indices. The pre-processing notebook handles data import, stacking, clipping, and scaling. So first we load TIFF files for each year into a 3D NumPy array using rasterio. We then clip the images to the Waltham Forest's boundary using a shapefile. All the values are rescaled to the 0-1 range. Then we normalize the entire dataset using 2021 as a reference year to reduce interannual variability from lighting or atmospheric differences. We then save this for easy reuse in the next steps. So next we can move on to the K-means notebooks. So we start by randomly sampling 50,000 pixels from the 2021 composite image to represent the typical spectral variability. These are scaled using standard scaler to normalize the features before clustering. We run K-means with a K of 4 based on our prior silhouette and elbow analysis. The clustering is unsupervised, so after clustering we inspect the outputs and manually label the resulting clusters. Based on what they visually correspond to, these labels are then assigned back to the full seed predictions for 2020 to 2024. A function maps each cluster to a color palette and creates a panel map showing year-on-year change. This makes it easy to visually trace urban dynamics like urban growth or green areas shrinking. Although this method is label-free and low cost, cluster interpretation is subjective and consistency over time can vary depending on how stable the spectral groupings are. The second notebook uses a supervised random forest model trained on ESA World Cover 2021 land use labels. We use 250 pixels per class stratified from World Cover, but within Waltham Forest only 3 classes were present in the sample: urban, vegetation and water, so these are overlaid on the 2021 stack and converted into feature vectors using 8 spectral features, the same as K-means. The model is trained with 300 trees and balanced class weights using an 80-20 train test split. Once trained, the random forest model is applied to the entire area for each year. We export yearly maps to compare to K-means. Random forest tends to give smoother, more semantically defined outputs. However, it's also more sensitive to small spectral changes, which sometimes leads to overestimating land transitions. So in this part of the notebook, we directly compare both models. The random forest model detects a 14% increase in urban area between 2020 and 2024. On the other hand, the K-means model suggests a 7.8% decline, mainly because its clusters are more reactive to subtle reflectance shifts, not strict labels. Next, we visualize change maps where red is urban gain and yellow is vegetation loss. As you can see, the random forest model picks up on more granular changes, but a lot of these may be false positives from minor pixel shifts, where K-means is more conservative, only marking larger structural transitions. This shows the trade-off between the two models. The random forest model trained on static labels offers consistency in class definitions, but is sensitive at the pixel level, producing more visible red-yellow noise in the change map. Meanwhile, k-means yield smoother maps but greater year-on-year variation in total class areas due to its sensitivity to spectral shift and threshold shifts. As part of this project, I also tracked the energy and carbon footprint of each stage. These were calculated using conservative assumptions for CPU power and UK electricity emissions. Total emissions were under 1 gram of CO2 equivalent, roughly the same as boiling a tenth of a kettle or streaming HD video for less than a minute. Pre-processing in k-means took slightly longer than Random Forest, so Random Forest actually had the lower footprint overall in this case, but the entire project had a very small footprint. But tracking this helps reinforce habits of low-impact computing. Using CPU-only collab, normalized pipelines, and avoiding redundant computations are key to this. Ultimately, this project doesn't aim to prove that one method is better than the other, it's about understanding how each one sees the urban landscape differently. Random forests offer categorical clarity and more stable outputs over time, which is great for applications where consistency matters, like policy reporting or change monitoring. K-means, on the other hand, reveals internal variation and doesn't rely on labels, which makes it valuable in data-scarce settings or where subtle surface transitions are important. The main takeaway is that the choice of methods shapes the narrative your map tells. Understanding those trade-offs helps us make smarter, more responsible decisions, both technically and environmentally. So thank you so much for watching. The full code, maps, and walkthroughs are all available on the GitHub linked in the description below. This project was a really rewarding way to apply machine learning in a real-world geospatial setting. Special thanks to Professor Michelle Samados, Weibin Chen, and Connor Nelson for the teaching materials for UCL's AI for EO course. I'm glad this assignment gave me the opportunity to explore a topic I genuinely enjoyed working on. Feel free to adapt the code for your own region or problem, and thanks again for watching.